We've organized this massive chapter into 5 logical conceptual layers. It should help you build a mental map of the material.
I like that. A map is essential when the terrain is this complex. So what does the roadmap look like? Lay it out for us.
Okay, we start at the most fundamental level. Layer 1 is quantum technology. This is the physics that, well, it changes all the rules of the game.
Okay.
Then layer 2 is advanced manufacturing and materials, so how we actually build the future.
Chips and printing and all that.
Exactly. Then layer 3 is power and spectrum integrity, so how we energize and protect all these new systems.
Right.
Layer 4 is operational systems and enablers. These are the tools that actually aid decision-making on the ground.
And layer 5.
And finally, layer 5, specialized warfare and countermeasures. This is where the rubber meets the road, in actual combat scenarios.
5 layers. From the subatomic all the way to the subterranean. Okay, let's not waste any time. Learner, take a deep breath. We are diving into layer 1, quantum technology.
And the documents, they describe this as the second quantum revolution.
Which immediately begs the question, what was the first one? Did I miss a revolution?
You're living in it. We're all living in it. The first quantum revolution really gave us the 20th century. It brought us nuclear power. It gave us lasers, the semiconductor chips in your phone, MRI machines.
So all the foundational tech we take for granted.
Pretty much. But those technologies rely on quantum mechanics in, let's say, bulk. We were manipulating billions and billions of electrons all at once to get a result.
So it's sort of like herding sheep then. You're controlling the whole flock, but not, the individual animal.
That is a perfect analogy. The second quantum revolution is different because now we are controlling the individual sheep. We are manipulating and controlling individual quantum systems, a single atom, a single ion, a single photon.
And the text makes a point of mentioning a specific threshold we've reached. It's called the standard quantum limit.
Correct. And that's a key term. The standard quantum limit is the absolute theoretical limit of measurement accuracy at these quantum scales. We're now building devices that operate right at that very edge.
And for the armed forces, what's the key takeaway here?
The key takeaway is this. This isn't about some kind of magic weapon appearing out of nowhere. It's a force multiplier. It enhances measurement. It enhances sensing, precision, and computation power. It takes them to levels that were, frankly, physically impossible before.
Okay, but to understand how it does that, we've got to get into the physics. The source text outlines 4 central tenets of quantum mechanics. These are the rules of engagement for this layer.
They are. And if you don't grasp these 4, the rest of it won't make sense. They're foundational.
All right, let's unpack them. Tenet number 1, wave-particle duality.
This is the one that really breaks our everyday intuition. In our normal lives, a thing is either a particle like a baseball or it's a wave like a ripple in a pond.
Mutually exclusive.
Right. But at the quantum scale, something like a photon exhibits the behavior of both a particle and a wave simultaneously.
So it's not just a little ball of light, it's also a ripple of probability.
Exactly. And that's so important because it allows us to do things like interfere with the probability of where that particle is. That's the very basis of how a quantum computer calculates.
Okay, that leads us neatly into tenet number 2, the uncertainty principle.
Heisenberg's famous rule. It simply states that you cannot measure the exact position and the exact momentum of a photon at the same time. The more precisely you know where it is.
The less you know about where it's going.
Exactly. There's a fundamental trade-off.
It sounds like a limitation, but I remember from the text that in cryptography, it's actually a feature, isn't it?
It absolutely is. It means you can't measure a quantum system without disturbing it. Which brings us directly to tenet number 3. And for an exam, this is critical for any security discussion. The no cloning theorem.
That sounds pretty absolute. No cloning.
It is. The theorem states it is impossible to create an identical copy of an unknown quantum state. Full stop. If you have a secure message encoded in a quantum state and some adversary tries to copy it,
They can't. They'll fundamentally alter it.
they destroy it in the process of trying to read it.
So, in a military context, that's the ultimate safeguard. If an enemy tries to intercept and copy your cryptographic key, they destroy the key, and you know you've been compromised.
Precisely. It turns the laws of physics into a burglar alarm, an unbreakable one.
And finally, the 4th tenet, the one that I think Einstein famously called spooky action at a distance. Entanglement?
Yes, entanglement. The text defines it as a beyond classical correlation. You can generate a group of particles, let's say 2 photons,
Yeah.
that are linked. They share a single quantum state. Now, even if you separate these 2 photons by 1,000 miles, a change in the state of one, it affects the other instantly.
Instantly. You mean faster than light?
The correlation is instant. It doesn't transmit information faster than light, but the connection is instantaneous. It implies that, well, that space isn't quite what we think it is. For the learner, just remember this definition. Linked particles, where the state of one determines the state of the other, no matter the distance.
All right, those are the four tenets. Wave-particle duality, uncertainty, no cloning, and entanglement. Foundational. Now let's apply these to the actual technology, the biggest buzzword in this whole sector, quantum computing.
Right, and this is where we see that massive, almost unimaginable leap in capability.
Yeah.
To understand it, you have to contrast the classical bit with the quantum bit, the qubit.
A classical bit is what everyone's familiar with. It's what our listeners are using to hear this right now. It's binary.
It's a switch. It's either a 0 or it's a 1. Voltage low or voltage high. Simple. But a qubit is different. It relies on that principle we mentioned, superposition.
So it's not just 0 or 1.
No, a qubit can be 0, it can be 1, or, and this is the absolute kicker, it can be both at the same time.
And this is where that concept of memory scaling comes in. The text really emphasizes this exponential growth.
This is the most important piece of math to remember for this whole section. In a classical computer, memory scales linearly. If you have n bits, you can store n bits of information. Simple.
1 for 1.
Exactly. But because of superposition, adding a single qubit doesn't just add 1 unit of storage. It doubles the complexity you can handle. So n qubits equals 2 to the power of n states.
Okay, let's just put that in perspective for a second. If I have, say, 3 classical bits, I have 3 pieces of data. If I have 3 qubits,
You are handling the coefficients for 8 different combinations all at the same time. Now scale that up. If you have just 300 qubits, you are handling more states than there are atoms in the visible universe.
wow.
That is the power of exponential scaling.
But actually building these things, I mean, it must be incredibly difficult. The text lists several specific hardware implementations. For the exam, the learner probably needs to know these. Let's run through the list of how we actually build a qubit.
Okay, the doctrine lists 7 main methods. First, we have superconducting circuits. This is the approach that IBM and Google are famous for. They create these tiny resistance-free current loops.
Okay, superconducting circuits. What's next?
Second, trapped ions. This is where you use electromagnetic fields to trap charged particles, ions, in a vacuum. You hold them perfectly still.
Trapped ions. Got it.
Third is photonic qubits. This involves using single photons traveling on silicon pathways, a bit like wires for light. Fourth, you have neutral atoms, where you hold uncharged atoms in place using what they call laser tweezers.
Laser tweeze. Okay, so that's 4.
Fifth is quantum dots. This uses an electron spin, whether it's spin up or spin down, inside a tiny semiconductor crystal. Sixth is artificial atoms, which is where you add just a single electron to a piece of silicon. And seventh, this one is a bit more theoretical. It's topological qubits, which uses exotic things called quasi-particles.
Okay, that is a heavy list. Let's just recap for the learner. Superconducting, trapped ions, photonic neutral atoms, quantum dots, artificial atoms, and topological. Now, having the hardware is one thing, but how does the computer actually, well, think? We talked about superposition, but the text lists for 3 other operational principles we need to know: entanglement, decoherence, and interference.
Right. So we've already covered entanglement. That's about linking the qubits together so they work as a coherent system, not just a collection of individuals.
Okay. So what's decoherence?
Decoherence is the villain of the quantum computing story. It is the collapse of that delicate quantum state back into a normal non-quantum state.
What causes that?
Almost anything.
Yeah.
Environmental noise, a stray bit of heat, radiation, a tiny magnetic field. It's the reason quantum computers have to be kept in these massive refrigerators, shielded from everything and cooled to just fractions of a degree above absolute zero.
So it's incredibly fragile.
Extremely. It's the single biggest engineering challenge they face.
All right, so that's the villain. What about the last principle? Interference.
Interference is how we actually get the answer out. When the computer is calculating, remember, it's exploring all the possible answers at once because of superposition. We design algorithms so that the wave functions of the wrong answers interfere destructively.
They cancel each other out.
Like waves crashing into each other and flattening out? Yes. And the correct answers are designed to interfere constructively, so they amplify each other.
So the right answer literally rises out of all the noise. That's
Yeah.
fascinating. Okay, let's move from computing to communication. Quantum communication.
The principle here is about using single photons as information carriers. You can send them over standard optical fibers, or you can beam them through free space, say from a satellite or a drone.
But there's a problem with optical fibers over long distances, isn't there? Signal loss or attenuation?
Right, and in a normal classical network, if the signal gets weak, you just use a repeater to copy it, amplify it, and send it on its way.
The no cloning theorem.
Exactly. You cannot copy a quantum signal, so you can't use a classical repeater. You need something called a quantum repeater.
How on earth do they work if they can't copy the signal?
They use teleportation. They use entanglement to transfer the quantum state from the incoming, weakened photon to a fresh photon without ever actually reading or copying the state itself.
So it preserves the security while extending the range.
That's the idea. It's a critical piece of technology for building a quantum internet.
And this kind of infrastructure supports what the text calls the killer app of quantum communications, quantum key distribution, or QKD.
QKD is the gold standard for future secure communications. It allows two parties to share a cryptographic key with an absolute guarantee of safety backed by physics. If an eavesdropper tries to intercept the photons that make up the key,
The measurement disturbs the system.
it changes the key's properties, the error rate spikes, and the system immediately flags the intrusion. Both parties know the key has been compromised and they just discard it and start again.
Incredible. The text also mentions two other applications here: blind quantum computing and quantum radar.
Right. Blind quantum computing is a very interesting privacy protocol. It basically allows you to send an encrypted problem to a quantum server, have it solve the problem while it's still encrypted, and get the encrypted answer back.
So the server itself never knows what the question was or what the answer means?
Never. Total privacy.
Yeah.
Then there's quantum radar. This is for detection in very, very noisy environments. It uses entangled photons in what they call probe and idler modes. Even in an environment with heavy enemy jamming, the quantum correlation between the photons helps it pick out a target where a classical radar would just see static.
All right, let's wrap up layer one by looking at the whole ecosystem. What's the strategic balance sheet here for the armed forces?
The advantages are pretty clear. Unprecedented speed for certain problems, mastery of optimization, think complex logistics, supply chains, weather modeling, and of course that unhackable security from QKD.
And the downsides?
The disadvantages are all engineering hurdles. Those extreme cold requirements, we're talking millikelvin temperatures, colder than deep space, the high cost, the extreme sensitivity to noise, that decoherence problem.
And there's one other thing mentioned, a major threat: Shor's algorithm.
Yes. For the learner, this is a critical point. Shor's algorithm is a quantum algorithm that proves that a sufficiently powerful quantum computer could factor very large prime numbers incredibly fast.
And why does that matter?
Because almost all of our current encryption, RSA encryption, which protects banking, military communications, everything, its security relies on the fact that factoring large numbers is incredibly hard for classical computers.
So it's a powerful quantum computer comes online.
It breaks RSA. All of our current secrets would be vulnerable. It's the Y2K of the quantum future, a ticking clock.
A major strategic threat. Finally, for this layer, who are the key players? The text lists several key Indian organizations.
Yes, for revision, you'll want to memorize these acronyms. First, QCAL, which is the Quantum Computing Applications Lab that's a partnership between MADI and AWS. Second, NMQTA, the National Mission on Quantum Technologies and Applications. That's the central government's big push.
Okay, QCAL and NMQTA.
Then there's QUAMAC, the Quantum Measurement and Control Laboratory, the National Quantum Mission, or NQM, which was approved in 2023, to really scale up the technology. And finally, and most relevant for the armed forces, the Center of Excellence at MCTE. Well, how? This is the specific Army node for all quantum research.
An excellent, thorough summary. That closes the book on layer one. We've covered the physics, the hardware, the applications, and the strategic implications. Now let's shift gears. We are moving from the ethereal world of quantum states to the very concrete world of atoms and manufacturing. Layer two?
Yeah.
Advanced manufacturing and materials?
Exactly. This layer is all about how we build the hardware that runs all the software we've been talking about. And we have to start with semiconductor device fabrication, or more simply, chip manufacturing.
The text calls this a physiochemical process. That sounds intense.
It is arguably the most precise and complex manufacturing process in human history. It involves creating billions of transistors on an integrated circuit, or IC, on a wafer, which is usually made of single crystal silicon.
This isn't like a car factory assembly line.
Not at all. It's a 6 to 8 week cycle of layering and etching over and over. And the environment it's done in is absolutely critical. They're called clean rooms.
And that's an understatement, right?
A massive understatement. Imagine a surgical operating theater, then make it 1,000 times cleaner, These are hermetically sealed environments, usually filled with pure nitrogen. The text emphasizes that dust is the absolute enemy. A single speck of dust on a silicon wafer is like a boulder landing on a city map. It just destroys all the circuitry beneath it.
There's a key metric mentioned in the text for this process. Feature size, or line width. What is that?
That's the width of the smallest pattern you can print on the chip. When you hear tech companies talk about a die shrink, it means they've found a way to reduce this number. Smaller features mean you can pack more transistors into the same physical space.
And more transistors means more power.
More density, more speed, better efficiency, all without having to completely redesign the chip's architecture.
The text helpfully categorizes the entire manufacturing process into 4 general buckets. What are the 4 pillars of chip making?
Okay, the 4 main categories of processing are, number 1, deposition. This is simply adding material to the wafer. You're vaporizing metals or insulators and letting them settle in incredibly thin films.
So adding layers.
Correct. Number 2 is the opposite, removal. This is etching, taking material away either with chemicals or with a high-energy plasma.
Adding and subtracting. What's third?
Third is patterning. This is the heart of the process. It's called photolithography. You use ultraviolet light, shown through a mask, to draw the circuit design onto a light-sensitive chemical you've coated the wafer with.
It's like photography for circuits.
A very, very precise form of it. And the fourth and final category is modification. This is where you change the electrical properties of the silicon itself, often through a process called ion implantation. You are literally shooting ions into the crystal lattice to change how it conducts electricity in specific places.
Deposition, removal, patterning, and modification. Got it. That's the cycle. Now let's look at a completely different kind of manufacturing. Printing. We are all familiar with 3D printing, but the text introduces a new concept, 4D printing.
This is a crucial evolution and a key concept for the learner. 3D printing is what we call additive manufacturing. You're building a 3-dimensional object layer by layer from a digital model, like a CAD file.
Right.
But 4D printing adds a 4th dimension, and that 4th dimension is time.
Okay, how does an object change over time? What does that mean?
It means you're using smart materials.
Yeah.
We're talking about things like hydrogels or shape memory polymers. These materials are designed or programmed to respond to an external stimulus.
A stimulus like what?
It could be heat, water, light, maybe a change in pH, an electric current, anything.
So you print it in one shape, a dormant shape, but when you expose it to that specific stimulus, it transforms into a second pre-programmed shape.
Exactly. It has functionality embedded in the material itself. The text highlights 3 key functionalities to remember: self-assembly, self-repair, and shape-shifting.
The applications for the armed forces here seem really practical.
Oh, very. Think about logistics. Take self-assembly. You could ship flat, compact boards to a forward operating base. When the soldiers there expose them to, say, water or heat, they fold themselves into furniture or even emergency shelters.
That saves a massive amount of shipping
A
volume.
huge logistics advantage. Or think about self-repair. A piping system in a remote location gets a crack. Instead of sending a team to fix it, the pipe material itself reacts to the pressure change and heals the crack.
And the text also mentions space structures and medical uses.
Yes. For space, you could launch a large antenna that's folded up into a tiny package. Once it's in orbit, the heat from the sun acts as the stimulus and it self-deploys into its full size. Medically, you could have a stent that travels through the bloodstream in a compressed form and only expands into its functional shape when it reaches the specific temperature or pH of the blockage.
It's material science that's acting as its own engineering. That's a great summary. That covers layer 2. We got the chips and we've got the materials. Now, layer 3, power and spectrum integrity. This is, I would argue, one of the biggest bottlenecks for the modern soldier. All this amazing tech is heavy and it all needs batteries.
Energy density is the holy grail. It's a constant struggle. The text focuses on the current workhorse, the lithium-ion battery.
We use them in everything from our phones to our vehicles, but for the exam, the learner needs to know the anatomy, what's actually inside the cell.
There are 4 main components you must remember. First, the anode. That's the negative electrode, and it's usually made of graphite. Second, the cathode. The positive electrode, made of a lithium metal oxide, like lithium cobalt oxide, or LiGo2A2.
Okay, anode and cathode.
Third is the electrolyte. This is a liquid that contains lithium salts, and its job is to allow the lithium ions to flow between the anode and cathode. And fourth is the separator. This is just a physical barrier, usually a porous plastic, that keeps the anode and cathode from touching each other and causing a short circuit.
And the working principle is a redox reaction. Can you break that down for us?
Redox just means reduction and oxidation. The easiest way to think of it is a shuttle run for lithium ions. When you're discharging the battery, using it to power your device, oxidation happens at the anode. The lithium ions leave the graphite, swim across through the electrolyte, and embed themselves in the cathode. Meanwhile, the electrons are forced to go the long way around through your device, and that flow of electrons is the electric current that powers it.
And charging is just the reverse.
Exactly. When you're charging, you use an external power source to force those lithium ions to swim back across the electrolyte and re-embed themselves in the graphite anode, ready for the next cycle.
So why lithium? Of all the elements, why is it the one of choice?
It's the most electropositive element on the periodic table. That's a technical way of saying it really, really wants to give up its electrons. This property gives it a very high charge density, a lot of power, and a very light package. It also has low self-discharge and no memory effect, like older batteries.
But the text is very clear that they have significant disadvantages.
Oh yes, they are fragile and have to be handled carefully. First is safety. They're highly inflammable. If that separator fails and the anode and cathode touch, you get a short circuit that can lead to thermal runaway, an unstoppable, very hot chemical fire.
We've all seen videos of that.
We have. Second is aging. They degrade over time, chemically, even if they're just sitting on a shelf. A 3-year-old battery just won't hold the same charge. And third is the strategic dependency. We rely heavily on imports for the raw lithium and other materials needed to make them.
So given those problems, what's the alternative? The text proposes fuel cell technology.
Right, and the fundamental difference to remember is that a battery stores energy, while a fuel cell generates energy on demand. It's an electrochemical cell that converts chemical energy, usually from hydrogen and oxygen, directly into electricity.
So as long as you have a supply of fuel, you have power.
Correct. It's like a chemical engine or a generator, but with no moving parts. The only byproduct is water.
What are the pros and cons there?
The pros are significant, very high efficiency, up to 60%, or even 80% if you capture the waste heat in a process called cogeneration. They're also reliable, completely silent, and have very low emissions. The cons are primarily cost. They often use expensive platinum as a catalyst, and the lack of a widespread hydrogen infrastructure, especially on a battlefield.
But the military applications are very specific and very compelling.
They are. The text highlights a few. For UAV endurance, a hydrogen fuel cell can potentially keep a drone in the air for 8 hours, compared to maybe 30 or 40 minutes with a lithium-ion battery. For the soldier's power load, it can reduce the weight of batteries a soldier has to carry for a 72-hour mission by up to 80%. It's a huge difference. And for vehicles, it allows for silent watch capability, running all the electronics and sensors without the noise and heat signature of an idling engine.
Now let's look at the other half of this layer. We've successfully powered the device, now we need to protect its signal. Let's talk about electromagnetic integrity.
This section covers two core concepts that are often confused. EMI, which is electromagnetic interference, and EMC, electromagnetic compatibility.
So EMI is the problem, EMC is the solution.
That's the simplest way to put it. EMI is the unwanted coupling of signals from a source to a victim. EMC is the engineering discipline of fixing it.
The text describes a trio that's required for interference to even happen.
Yes, for EMI to occur, you always need three things: a source, a path, and a receiver, which is also called the victim. The source can be natural, like lightning or a solar flare, or it can be artificial, like power lines, radio towers, or a force an enemy's jammer.
And the interference travels from the source to the victim via 4 specific modes. The learner needs to know these.
Yes, the 4 modes of coupling are critical. First is conducted. The noise literally travels along a physical wire or cable. This is further split into common mode, where the noise is on both lines, and differential mode, where it's on just one. Second is radiated. The noise travels through open space as a radio wave. Wires and the circuit board traces can act as accidental antenna, picking up these signals.
So conducted is through wires, radiated is through the air.
Correct. The third is capacitive. This happens when two conductors are very close together. The electric fields can actually bridge the air gap between them and transfer the noise. And fourth is magnetic, or inductive coupling. This is when the magnetic field from one wire induces a current in a nearby wire.
So how do we stop it? What are the shielding mechanisms to achieve EMC?
The goal is to break that path between the source and the victim. We have 3 main tools. First, reflection. You use a conductive material, like a copper mesh or a metal box, to essentially bounce the incoming radio wave back. Second is absorption. You use materials with high magnetic permeability, like ferrite, to soak up the energy of the wave and dissipate it safely as a tiny amount of heat. And third is grounding and bonding. This is about creating a low-impedance path to the Earth to drain any stray noise away from the sensitive circuit before it can cause a problem.
That concludes a very dense layer 3. We now have high-density power and we have clean spectrum. Now we can move to layer 4. Operational systems and enablers. These are the technologies that sit on top of all that hardware to help commanders make better, faster decisions.
And we start with something that affects every single operation: weather forecasting. The text notes the major shift away from manual calculations to what we now call numerical weather prediction. This uses supercomputers to solve complex equations of fluid dynamics and thermodynamics.
And for the armed forces, there is a very specific application mentioned that learners absolutely must know, the UNUMAN app.
Yes, UNINAN. It was launched in 2023 specifically for troops deployed on the border. It integrates a massive amount of data from the NCMRWF, which is the National Center for Medium-Range Weather Forecasting, satellites, radars, ground sensors, everything.
So for an exam, what are the key specs of UNUMAN?
Okay, key points are: it's a GIS-based application, a geographic information system. Its forecast window is crucial. It provides hourly forecasts for the next 72 hours. Its resolution is also key. It provides on-the-fly data for both surface and vertical levels, and it specifically covers a 200-kilometer transborder area. Its resolution is also key. And its utility is as a decision support tool. It's not just about whether it will rain, it's about providing detailed wind profiles for artillery fire corrections, for paratroop drops, for helicopter operations.
Excellent. The next enabler is global navigation and CORS. We all know GPS, or more broadly, GNSS, but the text makes it clear that for military-grade precision, standard GPS is not enough.
It's not. Standard GNSS has what are called error budgets. Tiny errors in the satellite's orbit, tiny drifts in its atomic clock, interference from the atmosphere. They all add up. The end result is a precision of about 10 to 11 meters.
Which sounds pretty good, but if you're guiding a missile or mapping a minefield, 10 meters is a disaster.
A total disaster. The solution described is the CORS network. That stands for Continuously Operating Reference Stations, a network established by the Survey of India.
So how does CORS fix that 10-meter error?
It's a really clever system. Imagine a network of permanent GPS stations on the ground that know their own position exactly, down to the millimeter. Each station constantly looks at the incoming GPS signal. It sees that the GPS signal thinks it's, say, 5 meters to the left of where it actually is.
But it calculates the error in real time.
It calculates a correction factor.
Yeah.
It then streams this raw data to a central control server. Users in the field can then connect to this server and get what are called RTK, or real-time kinematic services. The result: the accuracy improves from 10 meters down to plus or minus 3 centimeters.
That is a massive leap, from the size of a truck down to the size of a coin. Incredible. Okay, next on the list, presence technology.
This is a bit more abstract, but it's the foundational tech. The text calls it the digital handshake. It's a system that indicates the status and availability of a contact or a device on a network. Is it online? Is it busy? Where is it located?
So it's like the little green dot next to a name in a chat program, but for the battlefield.
Exactly, but on a much more sophisticated scale. It provides real-time location and identification. It can even utilize radiation emissions to automatically detect friendly or unknown devices entering a secure zone. The benefits are real-time situational awareness, improved security, and just faster, more efficient internal processes.
All right, now let's talk about robotics. Not just any robots, but specifically collaborative robots, or COBI-bots.
Yes, and the distinction here is very important for the learner. A traditional industrial robot is a huge, powerful machine. It works inside a cage, because if a human gets too close, it's dangerous. It might crush you. A cobot, on the other hand, is specifically designed to work with and alongside humans in a shared space. It's built with safety features from the ground up. Rounded edges, limited force and speed, advanced sensors that make it stop if it bumps into something or someone.
And the International Federation of Robotics, the IFR, defines 4 distinct levels of collaboration. What is that progression?
Okay, it's a ladder of increasing intimacy. Level 1 is coexistence. The human and the robot are in the same plant, there's no fence between them, but they're working on completely different tasks. Level 2 is sequential. Now, they share a workspace, but they take turns. I place a part on the jig, I move away, and then the robot comes in and welds it.
Okay, so they're working together, but not at the same time.
Correct. Level 3 is cooperation. Now they're working on the same part at the same time. The human holds the part while the robot drives in the screws. And the highest level, level 4, is responsive collaboration. This is where the robot is actively responding to the human's movements in real time. It anticipates your actions. It hands you the correct tool just as you reach for it.
That's amazing. Okay, the final enabler in this layer sounds like something straight out of science fiction, but the text treats it very seriously. Synthetic telepathy.
It sounds wild, I know, but the science is grounded in established neuroscience. It's defined as brain-to-brain transmission of thoughts without using speech.
How is that even possible?
Mechanism described combines two existing technologies. First, EEG, or electroencephalography, which uses a cap with sensors to read the electrical signals of the sender's brainwaves as they think of a word or command. That signal is then transmitted to the receiver, where a device using TMS, or transcranial magnetic stimulation, delivers a precise magnetic pulse to the brain to convey that signal nonverbally.
And the military application is obvious.
It's the ultimate in covert operations. Imagine a commando team being able to communicate silent orders, target left, move now, without opening their mouths or transmitting a radio wave that could be intercepted. In the traditional sense, it's hacking-proof communication.
That brings us to our final and perhaps most intense section, Layer 5. Specialized warfare and countermeasures. We are moving from the lab and the network straight to the battlefield, and specifically, the battlefield underground.
Yes, tunnel warfare or subterranean combat. The text uses the Gaza Strip as a very detailed and relevant case study of how an inferior force can use the subterranean domain to negate a superior force's air power and surveillance.
So for the learner, let's break down the key characteristics of that tunnel network as described.
It is massive. The text estimates it at around 500 kilometers. Concealment is key. The access points are deliberately hidden in civilian infrastructure, homes, schools, mosques. The depth is significant, 20 to 30 meters deep, which puts it below what many standard munitions can reach. The infrastructure is sophisticated, reinforced concrete walls, electricity, and wired communications to avoid radio detection. And the construction methods are low-tech to avoid detection. Pneumatic jackhammers and even pedal-powered diggers.
The text also does an analysis of the failure of the Iron Wall. What was that, and what was the lesson learned?
The Iron Wall was Israel's high-tech, 64-kilometer smart fence around Gaza. It was an incredible piece of engineering. It had a deep underground concrete barrier with sensors to stop tunnels, and above ground it had radars, cameras, and automated gun towers.
But it was breached.
It was. On October 7th, 2023, it failed. And the lesson is about asymmetry. Hamas didn't use high-tech weapons to defeat it. They used cheap, off-the-shelf commercial drones to drop small bombs on the observation towers and communication hubs. They effectively blinded the smart wall. Then they used simple explosives and bulldozers to create gaps. The lesson is that a high-tech static defense can be dismantled by low-tech, agile, and creative tactics.
And once you are forced to fight inside a tunnel, standard tactics and weapons just don't work. The text introduces a very specific countermeasure here, the sponge bomb.
This is a fascinating piece of chemical engineering. It's a non-explosive device. It's a container with two separate liquids inside, separated by a metal partition.
And how is it used?
The scenario is this. Your troops identify a tunnel opening. You don't want to send soldiers into that ambush point, but you also can't just leave it open for the enemy to pop out behind you. So you toss in the sponge bomb. When it's activated, the partition breaks, the two liquids mix, and a chemical reaction starts that forms a rapidly expanding, hardening foam.
So it seals the tunnel.
It seals the gap instantly. It's not about killing the enemy. It's about area denial. It blocks their movement. The text does warn, though, that the liquid emulsion is hazardous and can cause blindness or injury if it's mishandled by the user.
What about seeing and moving and communicating underground?
All standard equipment struggles. For visual, you need thermal NVGs. Standard night vision goggles amplify ambient light, like from the moon or stars. Deep underground, there is zero ambient light. So you need thermal imaging to see the heat signatures of bodies. For robotics, you never send a person in first. You send a robot. The text mentions the Iris, which is a small, throwable recon robot on wheels, and the MTGR, a slightly larger micro-robot that can climb stairs. For comms, radio waves are almost useless. They don't penetrate soil. So you either need wired robots that unspool a thin fiber optic cable behind them as they go, or you need to drop a chain of repeater nodes every few meters to daisy chain the signal back to the surface.
And how do you find these tunnels in the first place?
The BSF is using drone-mounted ground penetration radar, or GPR. It fires radio waves into the ground using either SFCW, stepped frequency continuous wave, or a pulse radar. It then analyzes the reflections to look for anomalies like voids or changes in soil density that could indicate a tunnel. Paired with GNSS for precise location, it can create a map of suspected underground structures.
Moving above ground now. The next topic in specialized warfare is camouflage technology.
The goal here is simple. Beat the sensors, not just the human eye. We now have multispectral camouflage, which is designed to conceal a soldier or a vehicle across the entire spectrum at once. The visible spectrum, infrared for thermal cameras, radar, and even millimeter wave sensors.
And then there's a leap forward mentioned called quantum stealth.
Yes, this is a material that utilizes lenticular lens technology.
Lenticular lenses, that's like those 3D stickers you'd get as a kid where the image changes as you tilt it.
It's the same basic principle but applied in a much more advanced way. The material is covered in these tiny lenses that bend the light waves around the object. It essentially creates dead spots, where the light reflecting off the subject simply doesn't reach the observer.
So it makes the object invisible.
Invisible to the naked eye, and also to IR and UV sensors. And the key advantage here is that it requires no power source. It's a passive material that's described as being paper-thin and lightweight.
We end this final layer on a rather somber note: entomological warfare.
The use of insects as weapons. The text categorizes this into three distinct types. First, using infected insects as vectors to spread diseases like plague or cholera. Second, crop attacks, using insects like locusts or specific beetles to destroy an adversary's agriculture and induce famine. And third, a direct attack, which involves using uninfected but aggressive insects like swarms of bees or wasps to simply inflict pain, cause panic, and disrupt operations.
And the legal context here is very clear.
Extremely clear. This is a direct and unambiguous violation of the Biological Weapons Convention.
That brings us to the end of a very dense Layer 5. We have covered a tremendous amount of ground today. Expert, can you bring it all together for the learner? How should they view this entire chapter, all 5 layers, as a whole?
The most important thing is not to see these as a long shopping list of gadgets. See them as a converged, integrated ecosystem. Layer 1, the quantum layer, gives us the new rules of physics and the computing power to break codes and optimize logistics on a scale we've never seen before. Layer 2, advanced manufacturing, is what allows us to build the silicon for those quantum computers and the 4D printed self-repairing infrastructure to support our forces.
Right.
Layer 3, power and integrity, ensures our soldiers and our drones have the energy density from lithium-ion or fuel cells to operate for extended periods, and that their signals are protected by proper EMI shielding.
The foundation.
Exactly. Layer 4, the operational enablers, gives those commanders the God's eye view, with precise weather from Inuminen and pinpoint location data from cores to make smarter, faster decisions. And finally, Layer 5, specialized warfare, is where all that advanced technology meets the brutal, asymmetric reality of the modern enemy. Whether it's sealing a dark tunnel with a sponge bomb or disappearing from a thermal site behind a quantum stealth cloak.
It's the integration of all these layers that truly defines modern and future combat. Learner, we hope this deep dive has given you the clarity and the structure you need. You have the definitions, you have the how, and you have the why.
Go into that exam with confidence. You know this material.
This has been the deep dive. Good luck and stay sharp.
Signing off.